So I'm sure A's going around really upsets everybody.
This hurts us as much as it hurts you. He gave us a week to the last.
You get to the point where you're sitting there and your entire schedule's been uprooted, you have a migraine, and you just go, nope. And you just open up Canvas, you 20. Look, I'm done. It happens. All right, so we were looking at this one. So sled, put a kid on it. These folks always like to put kids on these things. That way you can never make. So then if you have a dark sense of humor, you can't make jokes about it. But then we just put an adult on the slide one time and have some fun.
Or that one girl who dragged the suitcase to the airport with just
If I wrote a physics textbook, I'm not sure it would get published.
Yeah.
So that she probably just like come in.
I read that one.
Getting calls from the
Crazy.
public going, you can't say that.
I wonder if because like people writing this textbook so that.
Oh, I guess that's fair for you.
Our schedule sucks. I'm not gonna limit, I'm gonna be for like really.
Also, I always used to give extra points to the students who would answer questions fine like that. It's like, but in high school math, you always have Ronnie buys 42 cookies. Why?
I would buy 42 cookies. That's not unreasonable. 42 watermelons?
It's like you have 50 cookies and your friend takes 5 of them. How many do you have? I have 50 and they have a bloody nose. I always loved it when they would answer like that. Now, we're marking that. So the fourth slide, with tension.
Last night Alana bought fairy wings for us. Oh. I thought that was like literally like the physical children. She came in. Nice. I'm still deciding between. I waited my glasses today.
Okay, so we have a free body diagram. So find the tension in the core that's pulling the sled. Okay, well. You know our theta. 30 degrees. Okay, so we're going to say, let's just start with. So of course, it's a constant velocity system, so it's an equilibrium system. Now we know that means that the x component of tension, if you cosine of theta, then you're going to have a minus 0. So we put in the definitions of our forces. We do need to know what the normal force is. What forces do we have in the library? You have to use your weight. Small force.
tension Y.
Yeah, the Y component of the tension, don't forget about that. Okay, so normal force is going to be positive. And center of gravity is down. The Y component of the tension is up. And when we solve this, we're going to get a normal force equal to the weight minus the Y component of the tension. Okay, so we can plug that back in for the normal force. Put that, put it in there. Okay. So then the goal now is you end up solving for T to get the tension. Okay, so let's go ahead and we're going to leave on one side of the equation everything that has a tension in it. And then we can factor tension out of there. And the inner tension. Is going to end up being that. When you plug in all the numbers that you have, your tension is going to come out to be 43.1 newtons. Okay, so part B, what is the work done on the sled by the person pulling it for a displacement of 120 meters? Okay. Now again, I have a smaller diagram here. So what is our definition? Oh, and then we want to think that we have the displacement. So what is our definition of the work done by tension?
The tension force times the distance times the cosine of it.
So we have our dot product. The tension dotted with the displacement vector. And so yes, it's going to be tension, displacement, cosine theta between the two. And so when you put in your numbers, for 3.1 newtons, your delta R, 20 meters, and then you have the cosine. 33. So the work done by the tension. 4479 joules. Or about 4.5 kilojoules. Once we get to the work part, it's actually not that bad. Eventually you're going to get to the point where you're going to talk about work being done in terms of kinetic and potential energy. But when we get to the work energy theorem, you're going to see that it becomes important what you call like where you can make things zero. You take very literally where your starting height is, where your ending height is. So then part C. What is the total work done on the sled? Total work. Okay, what to either one. Work is being done in which ways? So let's go back up to the diagram. You just calculated work done by the person pulling the sled. What else is being done? Friction force. That's going to be a non-conservative force. And so it's going to be dissipative. So what you're going to have is the work done by the tension in the string plus the work done by the friction force. And essentially, you have this diagram all over again. So now you also have the friction force. Okay, so we need to know what the work done by the friction force is. Okay, so the first thing we need to know is what is that friction force? And we've already pretty much solved this. It's going to be coefficient minus T and theta. We solved that above. So then you put all your numbers into here. And that friction force is going to have a magnitude of 37.3 newtons. Okay, so then the work done by friction force displacement K delta R cosine of what?
0. Yeah, 180.
180. You could do 0 since they're both parallel, but you'd have to remember that the friction force is going to do negative work. And so when you put in your 37.3 newtons, your delta R of 120 meters, and your cosine of 180, you're going to get negative 4476 joules. So then the total work done on the system, for the tension, you have 4479 joules minus 4476 joules. You get about 3 joules of total work done. So again, work gets kind of depressing because you thought you put out that 1,000 joules of work. Your boss comes along and tells you only 3 joules was accomplished.
You need to tell that boss you need some wheels.
Okay, kinetic energy. So we're gonna look at where it comes from, but your equation that you're gonna use for kinetic energy over and over and over again is 1/2 mv squared. One half the mass of your object multiplied by the velocity it's moving at squared. Also keep in your head the idea of mass times velocity, because when we get to momentum, that'll make it a lot easier. Because you'll see that momentum is just mass times velocity. And so you're going to end up seeing that the first part of our work energy theorem. So this one is called like the work kinetic energy theorem. Is your total work done equals the change in your kinetic energy. We're going to expand on that to a more complete work energy theorem. But let's say we have an object being pulled by a force. Going some displacement delta x. What we end up with, we say, well, the total work of the system we're going to get the force delta x, cosine and theta between them. I went ahead and made them parallel, so we can just call that theta 0. Okay. And then F equals what?
Times acceleration.
Yeah. Okay, so we're there. We need something to put in place of that AX delta X. Where do you think we get that from?
Oh, it's.
You're about halfway there.
It's not gravity, is it?
No. How do I get to, how can I replace AX delta X?
Yeah, velocity, right?
Kind of. Velocity over time. How do I relate acceleration and velocity? Isaac Newton and all his unhygienic 1600s glory is disappointed in you. So, if you remember, kinematic equation. So then your AX delta X is going to be 1/2. The final minus the initial squared, which is going to equal 1/2. And then, of course, with this setup here, we can go ahead and say that, you know, there's no movement in the y direction. So this is just your generalized final squared minus 1/2 initial squared. We can plug that in for the AX delta X. And then we multiply through by the mass of the object. 1/2. The final squared minus 1/2. And the initial squared, where your definition of your kinetic energy ends up coming out, your 1/2 mv squared, that we specifically have here. We have a final minus initial, what do we have? Delta. The change in the kinetic energy. Okay. So you kind of want to make sure you remember your kinetic, your energy theorems. Your kinetic energy is your 1/2 mv squared. Because most of the time, you're going to want to start here and then start substituting in your kinetic energy, your potential energy. We're going to have several types of potential. Eventually, you're going to have like a larger work energy theorem where you're going to have like work done by gravity, work done by a spring. You know, it's all kind of in there together. Okay. So here we have a bungee jumper. I don't know why people bungee jump. It seems like you're asking for it at that point. People always tell me, "Are you afraid the bungee's going to snap?" I'm like, look at me. I know the bungee's going to snap. So the bungee jumper has a weight of 780 newtons. Descends into, jumped off a bridge or descending into some kind of gorge from an initial height of 182 meters. At a height of 111 meters above the ground, the cord has done negative 21.7 kilojoules of work on the jumper. What's the jumper's speed at that point? Okay, so let's kind of look at what we have here. There's your 182 meters. We got the bungee cord there. And then we still have 111 meters to go. In the positive direction of y. So in this case, total work is what? There's two types of work here. So the person starts way up high, they're falling. That's work done by what? Gravity. Plus work done by bungee cord. Yeah, let's think about work done by gravity. Okay, that is going to be force of gravity, delta y, cosine of the theta between them. And so the force of gravity and the delta y and force of gravity in the y direction make what angle with each other? 80. So that's going to leave us with a negative force of gravity delta y. Final minus y initial, so that's going to give us a negative 780 newtons. And what's the Y final minus Y initial?
It's like 1, 2 minus 111.
You just flip it. Because you're at your final, you're at 111. You started at the 182. So this ends up giving you 55, 380 joules. So the total work done is going to be 55,380 joules minus 1,700 joules, which is going to give 73,680 joules. So why did we need that? Why did we need that total work? Because the work is going to be your change in kinetic energy. So we're going to use that fact. But we can make this a lot more pleasant for ourselves. How?
Velocity initial should be 0, right?
Yeah, why?
Started falling.
Yeah, because before you jump, you're not moving. That's going to become 0. So we end up with 1/2 mv final squared. Okay, so let's start solving for that. Let's say we have v final squared will end up being 2 and the total work over the mass. You just take the square root of both sides. Okay, now, how do we get mass?
F equals MA and B delta.
780.
Ah, there you go. So that equals mg. Mass so you're going to have a mass of about 79.6 kilograms. Okay. 2 times 33 joules over 39.6 kilograms, square root of the whole thing. You're going to end up with a final velocity 29.1 meters per second. That's kinetic energy. Now we'll start looking at our potential energies. Gravitational potential energy. So we're just going to start there. Because you'll also end up at a point where you have an elastic potential, which is given by some kind of spring system. So this one, the basic idea, your gravitational potential energy is going to either be mg delta y or mg whatever height you're at. Because if you think about it, An object sitting up high is all potential energy. And that potential energy will change into kinetic energy as the object begins to move in free fall. So, let's say you have the work done by gravity. We said at the very beginning, your initial kinetic energy is 0. Now, you have a final kinetic energy because you can be falling and moving. So then the question is, where does all that initial kinetic energy go? Well, it's all stored in potential energy. You can think of potential energy as energy storage. Now, you notice that the change in kinetic energy is negative mg delta y, which is your potential energy. So then that means since your kinetic and your potential are going to be the reverse of each other, that means your change in potential energy has to be a positive mg delta y or mgh. So what you end up getting is, that means that those two are the opposite of each other. And so if you think the work done by gravity, your change in kinetic energy as you start out at 0 velocity and begin to fall, it's going to equal the negative of your change in potential energy. Well, that means that your change in potential energy is going to be the negative, is going to be the opposite of the work done by gravity, which means your potential energy increases as you move higher up. Okay, so big takeaway from that is as you're working with this, make sure you remember your potential energy, the idea of your gravitational potential energy, mass times gravity times how high you are. And if you want to lecture again for a week, yeah, because next week is class. We're going to have lab on Thursday.
We'll be here next week. We leave on Thursday.
We did. Are you gonna have pass next week?